Hello students, today we are going to continue our chapter 5. We explore about the chemical reaction, how to balance them in our earlier lesson. So today we are going to learn how to recognize different kinds of chemical reactions. Okay, all the different chemical reaction we can put together into certain categories, and once we know which category they belong to, if we happen to see some new reactions, we can predict some of the products, we can predict what would happen because they belong to the same group, right? So that's why it is important to recognize the different kind of chemical reaction. In the lab, we can look for the evidences of chemical reaction. When we mix two things, then we look for certain proof to tell that reaction has successfully taken place. Okay, so some of the evidences of the chemical reactions are, if you see the change in the color change is a strong evidence of a occurrence of a chemical reaction. Okay, if you have copper sulfate solution, pale blue color solution, you add ammonia into it, then it will end up making very dark Persian blue coloration. You make sure that, oh yeah, the chemical reaction has occurred because I saw a change in the color. Similarly, formation of a precipitate, right? If you mix two clear solution and then it result into a solid, that solid could be white or it could be color, okay, then it is the evidence of formation of precipitate, means we have a successful chemical reaction here. Okay, similarly, if you mix two things and you observe the evolution of gas bubbles, right? The bubbles are coming out of it. They may be less or more in the number. It does not matter. If you see the bubbles, it means the reaction has occurred. So we can take clues or hints like changes in the color, changes in the precipitation formation, or changes in the bubbles, right? We can track whether the bubbles form or not, and we can say the chemical reaction has occurred or not. Okay, so these are the evidences. Now let's look into these broad categories that we can divide or we can put our chemical reactions into. Okay, so the majority of the chemical reaction we will learn in this class fall into 6 categories. We have combination reaction, decomposition reaction, combustion reaction, single replacement, double replacement, and redox reaction. I'm going to explain you each of these categories, what character do they have and how do we recognize them. Okay, so let's go learn one by one. So a combination reaction is the reaction where two or more reactants, they combine to form a single product. If you have two or more reactant but they combine to become a complex one single product, we put them under the combination reaction. Okay, combination reaction might also be called as synthesis reaction. You are synthesizing one product from two reactants. And here are some examples shown here. Okay, like nitrogen and hydrogen, you mix them in 1 to 3 mole parts, you will get 2 mole parts of ammonia gas, NH3. Okay, calcium and bromine, when you react, you are getting calcium bromide, and these are the examples of combination reaction. Now, the opposite of that is the decomposition reaction. Okay, when a single reactant breaks down into 2 or more product, then such kind of reaction, we put them in a category called decomposition reaction. The one single complex reactant split into simpler substances, right? Several products out from them. Like in general, we can write AB breaks down into A and B elements, right? Or compounds. Then we call it decomposition reaction. Examples here, ammonia can break down into nitrogen and hydrogen. Right? This is a decomposition reaction. From one complex starting material, you end up making two simpler substances. Right? Sometimes we might need to use heat to run such reaction. For example, here potassium chlorate under heat will break down into potassium chloride, and it will also give away the oxygen gas. Okay, so this is a decomposition reaction. All the examples given here are balanced equation, as we already learned how to balance if they are not balanced there. The third type of reaction is single replacement reaction. Okay, now the name tells it. Okay, and we will go with understanding what does it mean. Single replacement reaction means one of the element or atom of a compound will be replaced by other. Okay, generally single replacement reaction where one element replaces another element in a compound. Okay, then they will make a different compound and a different element as product. Let us understand that with a general equation here, or you can look on the molecular view. Okay, we have A reactant, and we have BC compound. The BC compound is also a reactant. What will happen here is this A will come and combine with C, and it will kick out the B. What is happening is A will replace the position of B, and it makes AC. We have a new compound, right? We had BC earlier, now we have AC. It is a new compound, and there is another product, B, singled out. Okay, so we have two reactants giving here two products. Sometimes we may have more products if they further break down, but this particular example, we have 2 versus 2, where B is kicked out as A replaces B. So single replacement reaction generally have BC means they do have a pair, right? They do have a cation and anion. They are the compound. So we have a compound, and in the compound comes the element. Now a new element will break down that relationship of a compound and form a new compound with it, with the partner. Okay, so that generally takes place in the single replacement reaction. Let's understand with another example, a real example here. We have iron, right? And we have copper sulfate, where iron is the element, right? Copper sulfate is a compound because we have copper and polyatomic ion, right? We have cations and anions. This is an ionic compound. And iron is a pure element from the periodic table, right? Iron solely iron by itself. So when this element comes in contact with a compound, okay, it will replace the copper. Okay, the iron will replace the position of a copper, so it will make a new compound, iron sulfate, and copper is the one who is kicked out here. So the products are iron sulfate and copper. Okay, iron can replace copper because both of them have tendency of making the cation. Both are metal, right? A metal can replace another metal and form the compound. Okay, do not replace otherwise. Okay, I don't see any other way of replacing it. Okay, but sometimes if you have do not make the wrong combination. You always want to have the plus and minus together in a compound, then only it makes sense, right? So here we have iron that can make a cation, and we have a polyatomic sulfate that can be a polyatomic anion. So we have a neutral molecule. That makes sense, right? So we have here single replacement reaction. So let's look on the other one. We have here sodium chloride and bromine. When these two come, you can see here the sodium is generally the metal side, right? It can make a cation. The chlorine is the one non-metal, so it makes the anion, right? Something that we learned in earlier chapter. We use that information here. And now bromine is another non-metal. The non-metal will replace the position of a non-metal. And now it can make, now we can make sodium bromide, right? So chlorine is replaced by the bromine, right? So now that chlorine kicked out and it remains as a diatomic chlorine molecule. And after that, you can balance the equation, okay? So that is how the single replacement reaction take place. And always we write the cation first and then we write the anion, right? In a formula of a ionic compound, right? That's why we write FeSO4. Fe is the plus, SO4 is the minus. Na is the plus, Br is the minus. You cannot write Br and A. That doesn't make sense. Okay, just to be clear with you. Okay, so now let's look on double replacement reaction in the next slide. Oh, there is one more before we go to the double replacement. We have a combustion reaction. So generally the combustion reaction is where the reactant burns with oxygen of the air. Okay, whenever we burn something in presence of oxygen, we are talking about combustion reaction. For example, you have a ribbon of magnesium, you burn with oxygen and you make the acid, magnesium oxide. It is a combustion reaction. Those reaction of hydrocarbon we learned to balance in earlier lesson, right? That is also a combustion reaction because your C5H12, which is a pentane, is burning in oxygen and it makes carbon dioxide and water as a product, right? So every time if you see oxygen is participant, right? Oxygen is there as a reactant, it is a combustion reaction. A good hint to recognize this reaction. Okay, so every time I'm giving you a hint how to recognize that particular reaction, keep that in mind. So now the next one, this one was easy. The next one, more important, okay, that we will spend more time is double displacement reaction. Okay, as the name tells you, there are two pairs. That's why the replacement takes place and result into two products. Okay, so here double displacement or multiple products. Double displacement reaction is a reaction in which two compounds, this is what I mean to say, two compounds exchange their parts or partners, okay, atoms or ions, and to form new compounds. Let's understand this with example. Here you have AB compound reaction with CD compound. Now A will kick out the C and make a bond with D. So we have AD, one of the product. The C, that one is left, will make a bond with B, and we have here CB, another product. Okay, what you saw here is AB and CD, they just swap those partners, right? As if they were dancing and they swap their partners and keep on dancing. So you have two reactants, and in the picture shown here, two reactants swipe their partners, and after swapping they do have new products, right? If they still have AB and CD, we do not say it is a reaction. Okay, here AD and CB forms, which are new compounds than the starting material. So the reaction took place here. Let's see some real examples. Okay, so double displacement reaction, they can be of a couple of different types. So we are looking here three different types of double displacement reaction. Okay, one of them is precipitation. So double displacement reaction that results into formation of insoluble product. Okay, formation of a solid. If you have a solid, right, which is insoluble, if you mix two clear solution, out of that comes out a solid product, then we call it precipitate. So precipitate is a term for the solid that result after the reaction of aqueous solution. Okay, so precipitation reaction is a kind of double displacement reaction. If you mix, here is the example. Let's say you have a test tube that contains lead nitrate. Okay, to that you added the solution from another test tube that has potassium iodide on it. Then these two clear solution will react to form the product, which is a colorful product. Okay, so it is an insoluble compound, so we write here solid in the parenthesis to show that it is a precipitate. Okay, and side by side there will be a aqueous solution of potassium nitrate. This is a reaction that we saw in our earlier slide, so I'm going to show you. This is a picture for that. Okay, when you add the potassium iodide into lead nitrate solution, these two solutions will react and you will end up making a yellow, very colorful product of lead iodide. Okay, so that picture photograph was for this reaction, and it is a balanced equation right here. So let me show you how can I tell that this is a double displacement reaction. It is fun to see that, discover that. We have here lead, we have nitrate ion. This guy is positively charged, right? Lead is positively charged. Nitrate is polyatomic anion. Nitrate means, you might have memorized it, NO3, 1 minus charge is the nitrate. So we have plus here, minus here. Potassium iodide, potassium is a metal, so this can form potassium cation, and iodide is a non-metal, it makes iodide anion. Now, when you have plus minus here, now they are all in the aqueous form. Whenever we write aqueous, means they are dissolved in water. Okay, so when the compound lead nitrate is in the water, it will break down into cations and anions. Similarly, potassium iodide will break down into potassium ion and iodide anion. Okay, now you have a combination. Okay, now you have a chances to make a good combination. You have a positive charge and you have a new negative charge. This positive charge will be attracted towards this negative charge and it can make a compound. Similarly, the leftover negative charge will be attracted to the leftover positive charge, make another compound. Okay, so here lead was attracted towards the iodide and we have here lead iodide compound, right? The potassium with the nitrate plus and minuses, it form another compound. So what is happening here? The swapping of partners. Both of them swap their partners, right? And then they form new compound. How do we swap? Whenever we do swap, always the positive of the one group will get the negative of another group, because positive does not make sense. Negative they repel, they do not attract, right? That does not make sense. So if you write lead Pb and K, if you write I and NO3, that is totally wrong. Okay, so I'm just giving you a hint how to place them together, how to rearrange them together, how to exchange the partners. So now you have the lead and iodide, right? So we have a formula of lead iodide. Some of you might forget, like, how do I get this formula? How do I write it? The lead is with +2 charge, okay, because from here we saw NO3 has 2, means this subscript came from the lead ion. Okay, so lead has +2 charge. Iodine is the one that always has 1 minus charge. We learn this in most likely while learning ionic compound. And now we swap those integers to make a compound. So lead iodide, if you write it correctly, this is Pb and then I, right? And then I have got I here. The I gets that 2. So it is a coefficient 2 there. So the compound is PbI2. Okay, so this is lead iodide. Okay, I think that is a complete story of this precipitation reaction. Let us now show you another reaction, which is formation of gas. Okay, whenever we have carbonates, then with acids it will form some gas, which is also a double displacement reaction. Let me show you how. Let us say you have calcium carbonate, you have some chalk powder. Okay, you have some chalk. Calcium carbonate is the lime chalk. You add some hydrochloric acid into it, then that calcium will break down into positive ions calcium and negative ions carbonate. Okay, the HCl can also be broken down into H plus and Cl minus because all of them are in aqueous phase. Now you see the possible combination. You have plus here, you have minus here. So calcium will be attracted towards the chloride, make a bond, make a compound calcium chloride. In the solution will be left H and CO3, which will make HCO3, okay, H2CO3 actually, and that H2CO3 is not stable in the aqueous form, and then it will further break down into water and CO2. Okay, so in the reaction forms H2CO3, okay, but right away when this H2CO3 forms, it will break down into H2O and CO2. Okay, liquid water, and we have carbon dioxide gas. So this is also called a double displacement reaction, okay, because double displacement took place here. Swapping of those charges or swapping of those partners, took place here. Okay, now let's see the third example. Any neutralization reaction between acids and bases are also double displacement reaction. Now it will be a lot easier for you to see that it has plus and minus components. It has plus and minus component. So plus gets the new minus, right? The old plus gets the new minus, and we have an ACl with that combination, and H and OH mix water. So every time we have acid-base neutralization reaction, okay, here HCl is the acid and NaOH is the base. Okay, whenever we have acid and base reaction, it forms salt. So NaCl is the table salt, right? It forms salt and water. Okay, that is the general products of the acid-base reaction. All these acid-base reaction or the precipitation reaction and the reaction of carbonate with acid, all these are good example of double displacement. Okay, so learn these by heart. You can also practice balancing them by yourself. It is already balanced. Just start with the frameworks, unbalanced framework, and start learning balancing them side by side, because you already learned. You just want to be pro on that, mastering that concept. Okay, so I think let's see how many reaction we learned. Okay, so on precipitation reaction, I wrote that when you mix these two clear solution, you will make one insoluble compound, and you can write that as a solid over here with a subscript, right? I told you because we saw the photograph and we can talk about it. So in the lab, we can mix the two clear solution and find out the solid coming as a result, and we know what is it, right? But theoretically, just if we do not have access to the lab, and we have to answer that question theoretically, whether that will form a solution or a product, insoluble product, we can rely on solubility guideline. Okay, so we have some theoretical knowledge, and this is important slide. You want to memorize it, and I'm going to tell you how to learn this by heart. Okay, anytime you get a formation of ionic compound in the reaction, you break that ionic compound into cations and anions. You easily can do that, right? And then look on, if you have ammonium compound, means if the cation is NH4 plus, then they will always be soluble in water. If they are soluble, you write them in the subscript. I lose my pen. In the subscript, you write aqueous, right? If it is AQ, right, it means it is soluble in water. There is no exception for them. Okay. Similarly, those ionic compounds, if they have lithium, sodium, potassium, it means all of these guys are from the first column of the periodic table, right? If you look on the periodic table, all of them are group 1, alkali metal, and these are the ions from the alkali metal. Then all of the compounds, whatever they may be, if they have these cations, they are always soluble. We do not have any exception for them. Okay, right away you know that compound is soluble in water. You get that? Okay. So now, what if you have some other cations in the compound of a question? Then you look now on the anions of them. Okay, let's say something like you have copper and you have copper nitrate. Okay, and the question is copper nitrate soluble in water or not? Let's say this is the question. Okay, how to use this guideline? You look on, oh, my cation is copper. It is not from the group 1A, so I cannot talk about it right now. I have to now look on the anion to answer the question. My anion is nitrate, and from the solubility rule or solubility guidelines, if we have nitrates, they are always soluble in water. Okay, they are always soluble in water. There is no exception. It means this copper nitrate is a soluble compound. That's how we extract the answer, okay, the information. Similarly, if you have a compound that has a perchlorate or acetate, then all of them are always soluble in water. There is no exception of them. Okay, now let's move on. What if your anion are either chloride, bromide, iodide? All of them are from the same column, so you can remember one of them and then you can use similarly for others. So chloride, bromide, iodide, if you have them in the compound, then they are always soluble in water, but these guys have the exception. So you need to remember this exception. If it is silver chloride or mercury chloride or lead chloride, then these cations make them insoluble. So silver, mercury and lead chloride or bromide or iodides of them are exceptional. They do not dissolve in water. They are insoluble. Okay, so let me write these. The exception means these compounds will be insoluble in water. If they are insoluble, then in the equation we write lowercase s, right, to show that it is a solid, right? That is how we do. And now if your anion is sulfate, okay, again most of the sulfates are soluble except if you have barium sulfate or mercury sulfate or lead sulfate, now in this case they are insoluble. Okay, and in the equation we write S for showing those insoluble compound. Okay, that's why with this information, let me show you. Okay, with this information, going back on the earlier slide, I can tell that lead iodide will be an insoluble compound because lead makes that exceptional case, right? For the iodide, the lead iodide is insoluble in water. I come to know just looking on the theoretically the solubility rule. right? So solubility rule is very helpful for us to figure out. So this is something from your solubility table from your lab manual. Here it shows the combination of different cations and anions, whether they will be soluble or insoluble in water. Only one thing that might be confusing because of the symbol is here these S are the uppercase S. It means they are soluble. I means insoluble. Okay, this S is not for solid. Okay, this S is for soluble, I is for insoluble. Look, so let's see here. If you look for lead, right, lead on here, and you have, I do not have iodide, but I have chloride. Okay, they are on the same family. So lead chloride, will it be a soluble or insoluble? I go into that particular column. I find it is insoluble. I means insoluble. So I can say lead chloride is an insoluble compound, right? Similarly, if the question is the silver carbonate soluble or insoluble, then I go for silver here. I go for carbonate here. And I look into the corresponding cell, right? So I reach here, it is insoluble. I get that. Let's say if the question is asking me if the zinc chloride or zinc sulfate is soluble or insoluble. So I have a zinc here, I have a sulfate here. So the zinc sulfate is down here. It is S means it is soluble here. Okay, so here this one is uppercase S. Okay, do not confuse this with lowercase s. So zinc sulfate is a soluble compound. So we can use this table also in order to figure out our solubility. Okay, so we can play this learning check over here to predict the solubility of the compounds. Please answer this question. The solubility of sodium carbonate, it is a soluble or insoluble compound? You can pause the video. Okay. Now, let me go for the answer. You have here how to answer this question. You first break down this into two parts, cations and anions. You have sodium and carbonate. If you have sodium, then it says always soluble. So this is soluble, right? If you have sodium here, they are soluble. If you have lead, then you go and check for sulfate. Sulfate says all sulfates are soluble except barium, mercury and lead. That's why you need to memorize that solubility rule. And we have a lead here. This is an exceptional case. So lead sulfate means it is insoluble. Okay, others are soluble. Now ammonium phosphate. You have ammonium here, right? If it is ammonium, then without looking on what is the another partner, you can say this is soluble. You have mercury chloride here. Oh, all other chlorides are soluble, but mercury is the exceptional case. So again, the mercury chloride is an insoluble one. It does not dissolve in water. It remains as a solid there. Okay, so that is how we answer it. Predict whether the precipitation reaction will occur in the following situation or not. Oh, this is fun. Let's try this. We have here cadmium chloride and ammonium sulfide. Okay, so plus and minus make the compound. So we will have, okay, I'm using a text box, so my subscript will not work, but you will understand that. It's CD and I have S, and then I have ammonium, NH4, and then Cl. Right? You can balance by putting 2 in front of that. And yeah, okay. And now let's see. The question is whether the precipitation reaction occur or not. Ammonium chloride, this guy has ammonium, means it is a soluble one. So you have to go with physical state AQ here, right? It is soluble. You have here cadmium sulfide. This guy is insoluble, so it is the precipitate reaction and it forms a solid here. Let me go back and see if we have the cadmium on the earlier slide. That would be making us easy to see. Please help me over and let's go to the earlier one. My buttons are not working. Okay. Somehow. Okay, the slide. Okay, now it's working. Sulfide, right? And we had to look for the cadmium. Sulfide, we have a copper insoluble, lead insoluble. Oh, cadmium was not here. But if you had a cadmium, sorry, I choose the example that is not shown here. If you choose the cadmium, so it's cadmium sulfide, it will be a insoluble one, okay? Because generally the sulfides are insoluble except the ammonium ones and except the sodium, potassium, the group 1A. So that is insoluble, okay? So cadmium sulfide is insoluble. So now we write solid. This is a lowercase s in the physical state. Okay, I think I'm taking more time. I will go back and silver, a nitrate, sodium, carbonate. Exchange those partners. Once you exchange, you will get silver carbonate, you will get sodium nitrate. The sodium nitrate will be soluble because it has a nitrate. The silver carbonate is the one that is insoluble. So precipitation reaction takes place here. If you want to confirm, you can check the earlier slide. Silver carbonate, I think I showed you. Yeah, I did show you that is insoluble. Now, similarly on the third, we have here silver bromide, which is insoluble, exceptional case, so it will be a precipitation reaction. And then calcium nitrate is a soluble one. So when one of them is insoluble, we call it precipitation reaction, okay? So all three of them is a precipitation reaction. Okay, that was the good exercise on our predicting the products as well as whether it is precipitate or not. Now we can learn how to write the net ionic equation here. It is an important part. So net ionic equation generally we derive from the molecular equation. Okay, so the whole equation, the reaction that takes place between the two reactants and the products are forming, it is shown here with all the formulas, right, as the molecularities. We call this complete equation or molecular equation. When we have a molecular equation, we can break them apart, okay? We can break them into ionic equation if we place them in an ionic form. Okay, so when silver nitrate is dissolved in water in aqueous, it will break down into silver and nitrates, right? Magnesium chloride will break down into magnesium ion and chloride ion. Okay, what will be the charges in them? We have already learned about this in earlier chapters, so I expect you to know them. Okay, so silver always has +1 charge. Magnesium is from group 2, so we have 2+ charge, right? We know that. Now, we have here silver chloride and we have magnesium nitrate. Again, all these things that are on the aqueous form, it means they are solvated, they are surrounded by water in the solution. They are in the dissolved form, so we can break them down into cations and anions. Okay, but if we have something like solid or something like liquid or something like gas, okay, if the physical states are solid, liquid and gas, we cannot break them further into ions. Okay, so in total ionic equation, we write all of them as it is. So you see here, other things, I break them down into ions. They contain charges in them. AgCl was a solid, so I am not allowed to break them into parts. I have to leave that as it is. So this is the total ionic equation. Okay, now after total ionic equation, you can check here. We have nitrates on both sides. We can cancel that. We have magnesium ion on both sides. We can cancel that. And rest of those that we do not have the partners on the other side, we leave them as it is. So these are the net ionic equation. Okay, so we call them, those that we cancel out, we call them spectator ions, because these are just like the audience. They are just watching what is going around. They are not literally taking part in the formation of a product. Something new product is the silver chloride. So silver ion, chloride ion, these are the main character of the performance, and these are making the product silver chloride. Okay, so those will be in the net ionic equation. So our net ionic equation look like silver plus chloride gives you silver chloride. Okay, or you can write 2 silver ion gives you 2 chloride ion, 2 AgCl. Right? Oh, all of the 2 will cancel out because it's 2 everywhere. So this is the net ionic equation. Okay, this is how we write it. So if the question is write a net ionic equation, means you need to break down the molecular equation into individual ions, right? And then in the individual ions, you need to cross out the spectator ions, right? There will be something like solid, liquid, or gas as a product. Those you cannot break it down, and then you leave them, and then finally they will be the part of the net ionic equation. Okay, so we just learned how to write the net ionic equation. Let's summarize what we have learned in today's class. We saw first the combination reaction, and this funny faces will tell us how to read that. Synthesis or combination means you have 2 different simpler substances, you combine into a phase, happy phase here, combine into a complex substance. Decomposition means you split the complex substance into smaller, simpler substances here. Single displacement means you are replacing only the face here, keeping the head as it is. The face, the emotions is replaced here, right? Single replacement. If you replace the emotion as well as the head, then we get double displacement reaction. If you burn up the reactant in oxygen, then you have a combustion reaction, you will have a flame, you will have a very high energy, and you have the water molecule and the carbon dioxide gas, the products of them. Okay, so this is a very funny pictorial summary that summarizes all the different reaction we learned. We have a spatial reaction, we will cover that in a next class. Okay. Yeah, so oxidation and reduction we will learn in our next lesson. Thank you.